So the next talk has the title AGNES. I give the German pronunciation. Abstraction-guided framework for deep neural networks security. Please.
Thank you. I'm Akshay Dhonthi. I'm a PhD student at University of Twente and also an employee at Audi. And this is done with my colleagues Marcello, Eiermann, and Dr. Vahid Hashemi from Audi, and my supervisor, Dr. Hans Moritz from University of Twente. So today I'm talking about a security technique to identify some security risks in DNN, deep neural networks. I'll quickly give an overview of where this is used. Since I'm working at Audi, our use cases are more towards the perception system for autonomous driving vehicles, and we are looking into these cases where they're risky. I mean, there is high security risk because these are safety critical systems, like, for example, scene understanding or rules of engagement. We cannot develop systems without perception or deep neural networks involved. And it's important that we make sure that they work all the time perfectly. The problem here is that we train these neural networks with a very large data sets for a very small example with a small image size of 32 by 32 pixels with 3 channels. We already see like 2.4 million parameters to get like a very nice accuracy, and this is huge for verification, any verification or testing techniques to work. What we ideally expect from the network is to get like a given input image. It has to always predict correctly, but then there are some issues here because this cannot be always perfect. There are some reasons, many reasons, but I'm focusing towards security risks that can happen, and these things can be unknown biases that are in the network which cannot be seen because we train on a large data set which we don't know what it contains. And there can also be some intentional attacks. For example, the data can be somehow manipulated, and there is no way to tell because you do not have like a direct understanding from input to output of the network. So we have a network which is black box in the middle. There can also be some poor training data because there can be, if you do some statistic analysis, there can be imbalance in data because you always don't get all the data for all kinds of problems and classification, and this is really hard to get balance every time. So these things are called backdoors in the network, and we are trying to focus on identifying these backdoors. One of the real-world scenarios, this is the bus from Ingolstadt, the city where I'm working. So this kind of traffic signs on the bus as an advertisement can lead to wrong predictions. First of all, it's detecting that as a traffic sign, but then it is predicting entirely something different because of some disturbance on the image. And this can lead to some accidents that was not foreseen. And this is the kind of motivation on my work, and the talk is mostly divided into how the technique AGNES works. The tool AGNES works. So I try to go into like 2 steps. I explain the building blocks of the tool, and then about the overall framework, and then we see some results. So the first module is the artificial brain stimulation. This is a technique from 2019. What it does is, given this kind of system, we look into hidden neurons in the network and then stimulate these neurons, try to modify their values to see if it will lead to a misclassification. And the point is to finally get like a set of neurons that are considered compromised, and then we analyze it to get some understanding why this happens. Now the number of hidden neurons can be huge, so that's where my technique comes in. So we try to somehow abstract the set of neurons based on some clustering techniques. Now I'll go into the module 2. This is a clustering method, and we propose 2 different kinds of clustering methods. First one is the approximate based clustering. So you see on the left, this is the neural network, and then what we do is cluster them in each layer to get some groups, and then we identify the cluster representatives, which are the groups are in colored and representatives are highlighted. What we propose is 2 different methods. One is we try to only stimulate the representatives, and then find the compromised neurons from the representatives. This is the approximate method. And then the other is we use a technique called deep abstract, which kind of removes all the neurons that are part of the cluster by moving the weights into the representative, and then we use this abstract network to then stimulate and then find some triggers. Finally, I'm talking about triggers here. I just want to quickly show how the triggers are developed. So this is again from the module 1, the IBS, artificial brain stimulation. We do some optimization to find out the triggers based on the compromised neurons. Now, the reason we have these two different techniques is because we are dealing with larger networks, and the abstraction or clustering methods do not always work on industrial functions which are huge and also has complex layers. That's where the tool that we developed comes in. So we have a way of we try to find out the kind of layers that are in the network, and then based on the complexity, we then go into the different methods and all this. We try to find the right method for our approach, and this is done automatically. And we're also dealing with to make this generic, the tool to be generic, so we can handle the networks from different frameworks like TensorFlow and PyTorch, because we convert them into ONNX kind of version model, which is like a generic one, and then analyze this. And then based on the complexity, like for example, if the network has layers that are for beyond CNN, convolution neural networks are fully connected. If they are complex, then we go into the approximate method by flattening them out, finding the cluster representatives, then putting them back together, and these representatives go in different places and then stimulate each channel separately. And then if it's contains only CNN and FC layers, then for the CNN layers we convert them into fully connected, because the convolution networks are nothing but sparsely connected, fully connected networks, which means you can easily convert them, but this will put large number of neurons in the hidden layers. To reduce them again, anyways we do the abstraction where most of the non-necessary neurons are removed. And all these modules which in the tool are function agnostic, which means the clustering and stimulation techniques can be replaced with newer approaches. Right now we just took the state-of-the-art methods to do this. For the experimental setup, we looked into several different kinds of triggers. Something new that we tried is put some transparency properties into the trigger. We made it a bit more transparent, so that these triggers which are put in the Trojan network or the attack network are sometimes not seen when you apply this on the real data. And we actually looked into large model architectures and also considered state-of-the-art architectures like VGG, GoogleNet, etc. And then combination of benign models and attacked models, we did around 400 experiments for different kinds of triggers. And as you can see, the parameters that network we consider are very large, from 80,000 to 3 million parameters, which means most of the techniques that are that are currently there right now would not work even for abstraction or for security analysis. And to look at the results, we were able to identify more backdoors. These backdoors are nothing but the triggers that are meaningful based on analysis after we reverse engineer them. And these backdoors were, gave us better idea. Sometimes the techniques like ABS and Ernst neural cleanse, which are benchmarks for us, they could not identify some of the backdoors that are there. And with runtime, since we are abstracting the network, we are also able to reduce the runtime of stimulation. Then about the results on different triggers, like I said, since we played around with transparency, with the low transparency, which means the triggers are not seen easily. Since we are clustering and then stimulating, our chances of finding the backdoors were highly likely, and that gave better results. For the approximate simulation, the clustering rate is very important. So this is something you have to we have to find out manually, and this is where there is some room for improvement in the next phase of the project. For abstract method, anyways, the clustering is controlled based on the drop in accuracy, so we don't have issues in the other method. So yeah, this is the tool, and thanks for listening.
Thank you very much for the talk.
Thanks.
So we are 8 minutes late. So, yeah, please.
Does this tool also protect or try to protect against these adversarial examples where it's meant to look to human eyes like a 50 kilometers an hour sign, but it's interpreted as 90 by the car or something like this?
So adversarial examples are a bit different. They do not have triggers usually. They play around with the way the gradients are learned, and we focus on security risks. Adversarial risk, you need to have the access of the network, which is usually not the case. So if there is something manipulated in the data, and then these techniques work. For adversarial work, we are looking into robustness analysis more in a more formal method-based approaches, but this works on only small networks right now.
Thank you.
Okay, so let's thank the speaker once more.
Thanks.